Welcome, ladies and gentlemen, to a lecture on solving problems using conservation of energy. Today I'd like to take a closer look at conservation of mechanical energy by solving some problems using this tool. So one of the nice things about potential energy is that we can increase it slowly and then have it released at a much faster rate. Okay? So for example, we can think about carrying something really heavy up to the top of some height, okay, up to the top of a cliff or something, right? So say we have a hill with a cliff on this side, and we carry some big heavy object up the hill, okay? And we can do that as slowly as we would like. We carry the object up to the top of the hill, and then when we drop it, we can convert that gravitational potential energy into kinetic energy much more quickly, right? Much more quickly than we could carry it up to the top. Now, that doesn't seem like a very impactful scenario. It's interesting that we can store the potential energy slowly and then convert it to kinetic energy quickly, right? We increase it at low power. Remember, power is the rate of change of our energy. And we convert it to kinetic energy. We release the potential energy at high power, right? We convert it quickly from potential energy to kinetic energy. But again, not very impactful. Who really cares that I can carry something up a hill slow and drop it off the hill and then it goes back to the bottom fast? Who cares? But that's not the only example of storing potential energy slowly and having it released more quickly. Let's think for a second about throwing something, okay? So if I have a ball, and I have this ball in my hand, okay? When I go to throw the ball, I can actually only throw the ball as fast as I can move my hand with the ball in it, right? So as my hand goes through this arc and everything, when I release the ball right here, all the faster the ball is going to go is whatever speed my hand with the ball had in it. And then I let the ball go and it flies that fast, okay? Now, something like a baseball is a really ideal throwing object, okay? The size fits really well in our hands. The mass of it is heavy enough to counteract some of the forces of air drag that are on it, but light enough that we can still throw it really hard, right? If we think about trying to throw a bowling ball like a baseball, you'd probably injure your shoulder, right? But a baseball, it's light enough that we can really swing our shoulder and really get our hand moving fast while the ball's in it, and heavy enough that it has a high terminal velocity, right? Now, about the hardest that humans can throw a baseball is pretty much major league pitchers, okay? So we have this object that's almost perfect for throwing, and about the fastest that humans can throw it is a little over 100 miles an hour. We'll say 105 miles per hour. That's about as fast as somebody can throw it. And if you've ever seen somebody who can throw 105 miles an hour, that is really fast, and they have to throw it really hard. They get their whole body into the act, and it's all to get their hand moving as fast as possible at the point that it releases the ball. Okay? So that doesn't really allow us to store energy slowly and release it quickly, right? We have to give the ball kinetic energy at a fast rate, right, to make it go fast. We can't move our arm slow and then have the ball move fast when it leaves our hand. Okay, so we kind of have to give it the kinetic energy as fast as we want it to go. Now, throwing a ball isn't that important, but if you were a prehistoric human, throwing a rock or throwing a spear, that might have been a little more important, okay? If you have a really good arm, you might be able to hunt something like a rabbit by throwing rocks at it. You might be able to hunt some kind of small game by throwing a spear at it, okay? But you have to get pretty close to be able to throw a spear hard enough to have it go through something like I don't know, woolly mammoth hide or buffalo hide or something like that. If you want to try to kill the animal so that you can eat it, you have to get close enough to be able to throw the spear hard enough to go through its hide and everything like that, right? And that can be pretty dangerous depending on what you're hunting, okay? You might want to eat some things that if you get too close and startle it, it might not run away, right? What if you startle that buffalo and instead of running away, it runs right at you, okay? Or you're hunting a woolly mammoth and instead of running away, it runs right at you. It's pretty dangerous, right? But thousands of years ago, humans figured out that you could slowly load potential energy and release it quickly. Okay? Now, they didn't have the concepts of energy. They didn't know that's what happens. Okay? They didn't know that that's how the thing was working. But they did figure out that you could store potential energy slowly and have it released quickly. And to do that, they invented something called the bow and arrow. Okay? A bow is a relatively simple device, okay? We have the actual bow here, and we have a string on the backside. And the bow is just an object with these little arms here that can bend without breaking, okay? Now, over the course of history, humans have used all kinds of materials to make bows. But the only real requirement is generally that these arms can bend without breaking, okay? And that usually that it takes a relatively significant amount of force to bend the arms. Okay? Now, you can make a bow that bends really easily, but if you do that, you have a spring with a really low spring constant, so you're not actually storing very much potential energy in the bow, okay? So usually, we want this arm to have a pretty decent resistance to being bent, but we need it to be able to bend without breaking, okay? And humans have used wood, bone, resins, composites now, plastics, metals, all kinds of things, okay, to make bow arms. Now the string is attached to either end of the bow arms, and the string doesn't stretch, okay? So you may have seen maybe a children's bow where these arms don't bend, and this string is a piece of like elastic, almost like a rubber band in between. That's not how a real bow works, okay? And if you've ever seen those little kid ones shoot their little toy arrows, they don't work very well, okay? In a real bow, what I want from the string is that it doesn't stretch, okay? I don't want it to stretch at all. I want this fixed length of string, okay? So when I have a bow, I pull back on the string to draw the arrow, right? And my bow bends more. I'll draw it as best I can here. And my string is shaped like this, okay? And this is different from, let's see if I can draw the bow before I pulled the string maybe looked like this, okay? So now it turns out that if I consider this distance here, okay, right along this line right here, this distance D, this string will actually act, first off, it's an elastic object, right? I pull this back and it'll return to the shape that it was before I pulled on it, okay? But it turns out that this string is going to actually obey Hooke's law to a decent approximation, okay? It actually looks like, if this is D, if we just had a spring like this, squished by the amount D, okay? That's actually how this bowstring will behave, to at least a decent approximation for simple bows like long bows or recurve bows or that type. The more complicated compound bows that exist today have some pulleys and things at the top to change how much force you have to pull on the string with, specifically so that it does not obey Hooke's law, so that I can draw the string back and hold it back here at the draw with a tiny amount of force, but then there's a lot of force in the area kind of as I pulled it from like here to here, and that's where the arrow's getting its energy from. Okay, that's what those pulleys on a compound bow do. For a real bow, if I draw it back to full draw like this, it's usually fairly difficult to hold it like that, okay? If it has a heavy draw weight, and the draw weight is how much force I have to pull it back some amount, okay? So to pull it a distance d requires some force. We'll say the force of the pull. And that's equal to the force that this elastic object would have, right? Minus kx. And the draw weight of the bow is k, okay? And for a bow with a heavy draw weight, it's usually hard to hold it at a full draw like this, because the further I pull it back, the harder the bow pulls, right? That's what Hooke's law says. The further I pull the string back, the harder the bow tries to pull my hand back to the equilibrium point, okay? So I draw the string back this distance d, and then I use conservation of mechanical energy, okay? So I say ui plus ki plus w nc equals uf plus kf. So if I draw the arrow back and hold it for just an instant there, I have no kinetic energy, right? The arrow comes to a rest. But I do have potential energy in the string of the bow, and that is 1/2 k d squared, okay? Because we pulled it back this distance d. We'll idealize this for a second and not consider any friction or anything like that, and say that the bow is able to transfer all of this potential energy into the arrow. Then on the other end, when the bow returns to this point here, this equilibrium point, I don't have potential energy anymore, right? The x in 1/2 kx squared, this x becomes 0. And so I don't have potential energy, but I do have kinetic energy of the arrow, okay? And then that tells me, let's put it up here. Up here at the top, I'll write Vf equals kd squared over m. All in a root, okay? So that's for our idealized case. And what's interesting about this, or what makes this so useful to people, is that I can draw the bowstring back as slow as I would like, okay? As long as I draw it back to some distance d, I'll get the same velocity, okay? So I can have a bow that has a really big k, so it's really hard to pull back some distance d. But if I get it back to that distance d, it doesn't matter how slowly I got it there. The speed of the arrow will be the same when it leaves the bow, okay? So I can store this potential energy slowly, and then I just let it go, and the potential energy is turned into kinetic energy of the arrow really quickly. Now, human muscles oftentimes are much, much stronger in a slow application of strength than if I try to make them act really, really quickly. Okay? So, I can pull this back, I let it go, and what I get is an arrow that flies much, much faster than I could ever hope to throw it. Okay? Not only that, it's much faster than anyone could hope to throw it. So if I have a terrible throwing arm, that doesn't matter here at all, right? If some guy has a great throwing arm, maybe he can hunt rabbits or something like that with rocks. But if I have a bow, now anyone, not just the guy with the great throwing arm, anyone in the tribe can go hunt game as long as they can pull the string back on the bow, okay? And this ability to store potential energy slowly and release it quickly dramatically changed hunting for prehistoric people, okay? As animals could be killed from further away with lower risk of injury to the person that was hunting them, okay? And this greatly affected the ability of humans to secure enough food to survive and to thrive in the prehistoric world, okay? And this whole contraption and all the effects that came from its invention hinge on the use of elastic potential energy and the fact that I can store it slowly and release it quickly. So now the truth of the bow, if we can consider this example a little more closely, is that there is some non-conservative work going on, right? So if I rewrite my equation here, so that I have ui plus ki plus w nc equals uf plus kf, okay? The truth is that this is not zero, right? And that it's really hard to write down the friction forces, the amount of movement that the bow has. So if you watch a bow fire in slow motion, it doesn't get to this exact position and stop, okay? It overshoots a little bit and the arms kind of wobble, so they might go out to like here, and they kind of vibrate, okay? And the string vibrates. That's all energy that doesn't go into the arrow, right? Because the bow wasn't moving before, and now I have different pieces of the bow moving around, so parts of the bow have kinetic energy, right? The bow actually is heated. There's friction going on in the arms here, okay? Now, we might not notice the heat if we put our hand on the bow. It's not heated by that much, but there is energy going into actually heating the materials here. And so there's a lot of energy that's kind of lost along the way, and it's really hard to account for, okay? So what we end up doing is we know that this much energy is stored when the bow is drawn, right? It's drawn some distance d, we have this much energy stored in it. And then what we can do is measure the speed of an arrow as it comes off of a bow. And we can do this a bunch of times, and we can see that work non-conservative is equal to, and we can see that it's some percentage of the energy that was there at full draw, okay? So say it's equal to 30% of 1/2 kd squared, okay? So 30% of our energy is lost. Now, to write this mathematically, I would say that this is equal to 0.3, first off negative because it's lost, right? Negative 0.3 times 1/2 kd squared, okay? And then I would put that into my conservation of energy equation, okay? This is the efficiency of the bow. How efficient does the bow transfer potential energy into kinetic energy, okay? And this is affected by a lot of things. It's affected by what the bow's made out of. It's affected by the shape of the bow. It's affected by the string that's on it. It's affected by the mass of the arrow. It's affected by mass of things that you might attach to the string, like maybe a little bead to help you knock the arrow in the right spot every time. It's affected by a lot of things, okay? And for a modern bow, a simple, like a recurve or a longbow, this efficiency is usually around, I think it's around 70%-ish. So this means that about 70% of your potential energy ends up as kinetic energy. So this, we can see from this equation, if 30% is lost, that's the same as 1/2 kd squared. Okay, I can factor out all this, and it's 1 minus 0.3, okay? But this would be the same as just writing 0.7, right? So that's where we get this efficiency. This bow would be 70% efficient at turning potential energy into kinetic energy, okay? And we can do this for all kinds of things that store energy. We can talk about an efficiency, how efficiently they can transfer that stored energy into something like kinetic energy, all right? In this case, the kinetic energy of the arrow. But even with this efficiency factored in, I can still just adjust K so that in the end I get an arrow that flies much, much faster than I could ever hope to throw it, and still have a bow that a wide range of people can draw, and I don't need some kind of elite athlete caveman with the best throwing arm in 10 tribes to be able to try to throw something hard enough to hunt an animal. So now let's move on to another example. And let's get back to Jim Bob. Okay, so from prehistoric man to, well, Jim Bob, who's I guess isn't that much different. All right? So Jim Bob is stepping it up on his next jump. He's going to do a jump on his skateboard by going down a smoothly curved 10-meter tall ramp that transitions into a curved 3-meter tall launch ramp. How fast will Jim Bob be going when he leaves the launch ramp? Okay, so what do we have? Jim Bob has a skateboard, and he has this curved ramp to give him huge speed on the skateboard, and then he's going to go off this jump at the end, okay? He has, this ramp is 10 meters, okay, so Jim Bob's really going hard here. And this ramp is 3 meters. So we want to do this, and then the question asks us, how fast, right? How fast will Jim Bob be going? So let's call this tall one H1, and let's call this short one H2. Then what we know is H1 equals 10 meters. H2 equals 3 meters. And we want to know what's VF. Okay, so we're going to use conservation of mechanical energy here. We like to use this pretty much any time that we can because it's easy to use, right? So we're going to use that, and that is C of ME, conservation of mechanical energy. Okay? So then we go through the terms. Initially, is there a potential energy? There is. mgh1. If he starts from rest, then there is no initial kinetic energy. All right? That's 0. We have Jim Bob going down this on a skateboard. We're going to approximate it as sliding without friction. So we have no non-conservative work. So then we can move over to the end. At the end, do we have a potential energy? We do. It's mgh2. Okay? Notice by defining these energies this way, I've made the ground my 0 in my coordinate system, right? So I have standard x, y, and I've made the ground 0 in this coordinate system. And you can see why oftentimes when we use energy, we don't bother writing the coordinate system, because the picture or the conceptualization of the problem makes it so obvious what the choice would be. Okay? So it's usually so obvious what the choice is and what the choice should be that we don't bother to write it. Okay? But you can see there is a coordinate system chosen. Okay? And the fact that I'm using this as the potential energy tells you what that coordinate system must be. Okay, so we have this potential energy at the end as well. And then do we have a kinetic energy at the final? Oh, what have I done? I said this was 0, but then I wrote it in anyway. Sorry, no kinetic energy because we start from rest. No non-conservative work because there's no friction. We said we do have a potential energy at the end. Okay? All right, now I'll try to write what I actually say here. At the end, do we have a kinetic energy? We do, right? We know that Bob is going to launch off of this thing, and in fact, we want to know how fast he's going to launch off of it. So at the end, we do have a kinetic energy. Okay. Now all I have to do is solve for V, right? I see that M is everywhere. It's going to cancel. I see that I can bring this term over to the left, right? And that I can multiply the whole equation by 2. And if I do that, I get 2g. I'll have h1 minus h2, right? Both of those would have a 2g in front of them, equals Vf squared, which tells me that Vf equals 2g h1 minus h2. Units, we have meters per second squared. Then we have meters minus meters. That's all in a root. So we get meters per second. The units work. That's nice. Sanity. We can see that Vf is bigger if G is bigger, right? And we can see that Vf is bigger as H1 is bigger. Those both make sense. And also that Vf is smaller as H2 is bigger, right? So if I had a bigger acceleration from gravity, I would have a higher speed at the end. That makes sense. If I made the ramp taller with the same acceleration from gravity, then I would be going faster when I got to the bottom of the ramp, right? That makes sense. And then my speed goes down as H2 goes up. So if I make this ramp taller and taller, this launch ramp, I go slower and slower off the bottom of it. Well, that's because I have to go uphill, right? And I know if I'm just coasting along, I'm going to slow down as I go up the hill because gravity's pulling me down the hill while my velocity's trying to go up the hill, right? So that makes sense. And indeed, if I make H2 equal H1, then this V final becomes 0, right? And then I have a half pipe, right? And the whole deal with a half pipe, where these two ramps are the same height, is that I just go back and forth, right? I go to this side and then I go back to this side. That's the whole deal with the half pipe. Is I don't launch out the end of the half pipe. I just go up to the top and then I go back down the other way and go to the top the other way, okay? So all of our sanity checks make sense too. And then in the end, if we plug in numbers, we get the Vf equals something. 12 meters per second. So now let's consider one last example. Let's consider a block sliding down a ramp with friction. So it says consider a 2.3 kilogram block sliding down a 36-degree ramp with coefficient of kinetic friction of 0.37. If the ramp is 1.24 meters tall, how fast will the block be going at the bottom? Okay, so y equals 1.24, m equals 2.3 kilograms, theta equals 36 degrees, and mu sub k equals 0.37. Okay, so we're going to solve this one with conservation of mechanical energy. Ui plus Ki plus W and C equals UF plus KF. All right, so initially, do we have a potential energy? We do. It's mgy, okay? The block is some height y above the ground. Do we have a kinetic energy at the beginning? If it starts from rest, we don't, okay? So we have 0 for kinetic energy. And then, do we have non-conservative work? In this case, we have friction, so we do, right? And we know that W and C is equal to friction times the displacement x. We'll call the length of this ramp x. Okay? Friction dot displacement. So that is going to be equal to mu sub k, right, times the normal force, which is going to just be mg, okay? Or sorry, the normal force is mg cos theta. And then the displacement, x. Okay? And the dot product doesn't add another cosine theta because friction and the displacement are along the same axis, right? But it does add a minus sign, right? Because friction points this way and the displacement points this way. So we have 180 degrees. And fkx cos phi, where phi is the angle between the displacement and the friction, equals minus f sub k x. So then we have our non-conservative force in our equation here, mu sub k x mg cos theta. And remember, this cos theta is from the normal force, okay, not from the dot product. And then that's equal to potential energy at the end. We don't have any, okay, the ground we decided to make 0, times the kinetic energy, 1/2 m vf squared. Now if we look at the geometry of our thing, we have a triangle like this. SOHCAHTOA tells us that sine theta equals y over x, okay, opposite over hypotenuse. So this x is equal to y over sine theta. So we have mgy minus mu sub k x mgy, and then over sine theta, and we have a cos theta, so cos over sine is cotangent theta equals 1/2 m vf squared. And then notice that the m's all cancel. And I can multiply by 2 to get rid of the half. And I'll end up with 2 gy, that's in both terms, right? Times 1 minus mu sub k x. Oh, whoops. I still wrote the x up here. That's why. My mistake. We replaced the x with the y over sine theta, right? So we have 1 minus mu sub k cotangent theta, right? And again, I knew that the x wasn't right because I had something here with no units and I was subtracting something with units, right? So the x obviously wasn't right. That's all going to be in a root. And that's going to equal V final. And then units are meters per second squared times meters, all in a root, just meters per second. Sanity, VF up as G up, VF up as Y up, and VF down as mu K up. Okay? So if our acceleration from gravity is bigger, we're going faster at the bottom of the ramp. That makes sense. If I make the ramp taller, I'm going faster at the bottom of the ramp. That makes sense. And if I make friction stronger, I'm going slow at the bottom of the ramp. That makes sense. Okay. And notice that our answer here is the same answer that we had in the last lecture for sliding down the frictionless ramp, right? This first term is that answer minus this term that came from friction, right? This term from friction gave us this minus mu sub k cotangent, okay? So we have just the answer with no friction minus this correction to the answer that accounts for friction, okay? And then if we plug in numbers, we get some number. I don't really care what it is. We get some number at the bottom of the ramp. So that concludes our lecture for today. We got a nice look at just how powerful our new tool is, and you'll get additional chances to practice using it on the homework.